So I might as well use the problem that we were doing on Monday, and I think my function, and you can see my screen. You can see my Desmo screen. Yeah, nice. I think my function was x over 1 plus x, right? And we were looking at the point 1 comma 1/2. Now I had a fixed point there, right? But then I wanted to create an arbitrary point on this, a second arbitrary point, right? Now, so on the screen that I gave you on the recording that I just posted this morning, I'm using two arbitrary points, okay? A comma f of a. So I'm going to just use I'm going to use that second arbitrary point as a comma f of a. Again, it's different on the recording I gave you because on this one, on this particular problem, they give me a fixed point, right? And I'm trying to figure out that tangent line at that fixed point, okay? And you see this thing's prompting me for a slider. And so I can control that slider. You can see that point changing on my curve by me sliding the slider with my mouse or sliding the point, right? So sliding that arbitrary point. And you can visualize the secant line right through my blue point and my green point. So that's what I want. I want to be able to put those two things together. Okay, so what's my equation of my line? Does anybody remember the equation of a line? Let me get my OneNote open here. Anybody tell me the equation of a line, even the middle school version of it, if you must.
Y equals mx plus b.
Beautiful, and that's our middle school version. That's what we want our final answer to look like. But we want to use our point slope version, right? Which is y minus y sub 1 equals m times x minus x sub 1. Right? And so x1, y1 is an arbitrary point, right? x1, comma, y1, for us, a, comma, f of a, right, is an arbitrary point. Random, right? It can move, it can change. And, I'm sorry, is a fixed point. Is a fixed point. On our dynamic one, it's going to be an arbitrary point. So for us, it's 1 comma 1/2, right? And y is f of x, right? Is that x over 1 plus x. More importantly, is xy is what? What is xy? What is this combination of xy? What is this combination of xy? Just got an idea there. By the way, it's the same xy and y equals mx plus b, right? It's the same exact xy as what is xy? Say it again.
Is it the coordinate?
Say it one more time. Is that Markins?
Yes.
Yeah, one more time. What word are you saying? I just don't. I don't hear too well. And
can you hear me? Excuse me. Is it like the axis and the? I don't really remember it.
So you're getting at what I want. How I want you to think about it. It's every point. So xy it stays variable, right? So it's every single point on the line, including that arbitrary point. What we really want to think about, and I don't want to get confused these two y's together. What I want to think about is the slope of the secant line, right? So I'll say m sub secant, right? The slope of a secant line, and that is y2 minus y1 over x2 minus x1. And for us, that's going to be f of x minus 1 over x minus 1/2. I want to keep my arbitrary point, right, as the x sub 2, y sub 2. And of course I can fill that in, right? I have what? I have x over 1 plus x minus 1 over x minus, oh, I made a mistake there, right? I switched my x and y. Sorry. Wake up, Robert. Right, 1/2 is a y value, right? And 1 is an x value. Sorry about that. And I think did we do this? We did this last class, right? Yeah. And so I want to use 2 times 1 plus x over 2 times 1 plus x. And since we did it last class, I'm just going to go right away to a quick version. 2x minus 1 plus x over 2 times x minus 1 times 1 plus x. Yeah, I remember doing this, right? And then I think I get x minus 1 upstairs, right? And again, this is still my secant slope, right? With x is getting closer and closer to what? This is my secant slope with x is getting closer and closer to what number? I'm asking. Oh, I gotta put my chat on, sorry. If I'm ever ignoring something you put in the chat, just say, Robert, is your chat open? So I want to make sure I have that on in case you want to talk to me that way. What's up? What am I looking at? Oh, I was there. Hold on a second. Getting some family distraction here. Oh, yeah. I love that place. Yeah. Yep. Okay. Yeah, so if I'm ignoring your chat because I just accidentally closed it, let me know. What point am I getting closer and closer to? Where am I interested in the tangent line on this? Where am I interested in the tangent line?
Is it 1 and 1/2?
Yes, exactly. That fixed point, right? I'm going to decide I want to know the slope of the line that goes through one point on the curve. And I can't do that, right? I can't do that. Well, we're learning we can with a limit, right? So we're learning that we can with a limit, but then we're going to learn we can with a derivative. That's the valuable one. So, but when I finally cross this piece out here, right? This is my m slope tan. At 1, no, this is important. It's still my secant line close to 1. Okay, but that's the one I'm going to use for my secant slope, right? I'm going to use that one for my secant slope. Nice. So I need my equation of my line, right? So what am I doing? I'm doing y minus 1/2 equals my m sub sec times x minus 1, right? And that m sub sec, or the m sub tangent, right? This is m sub tangent. I'm going to use that simplified version. I can use the whole version, and maybe I will. Maybe you should see me write that once at least. I need f of x minus 1/2 over x minus 1. So there it is. And this is exactly, right, this is exactly my y minus y1 equals m times x minus x1. And that's, so this one, if you're going to get the mathematical tattoo, that's a good one to get. But probably 9th grade or whenever you took Algebra 2. I'm not promoting tattoos, but and students ask me, if you ever got a mathematical tattoo, what would it be? I said, a decimal place, a decimal. So this is what I want to put into my dynamic tangent line here. How we doing? Any confusion here, aside from me trying to throw you off because I'm making mistakes every now and then, but correcting. Everyone's okay? Okay. So I want to put that dynamic tangent line in, right? So I said y minus 1/2 equals my f of my slope, right, which was f of x. I want to keep it general whenever I can. Minus 1/2 highlighted all divided by x minus 1 all times x minus 1. You can see there's a problem even in the equation to put in 1. I can't, right? What did I do wrong? Oh. Sorry. I want f of a. I want that arbitrary point. Fixed point, right? And then a. This will allow me. What did I do wrong? I did something else wrong. Sorry. Yes, I know what I did. Everything should be a f of a. So if it's a y value, it should be f of a. Sorry. And if it's an x value, it should be a. Okay, I'm making a mistake somewhere else somehow. Give me a second. Oh, all right. Sorry. One more time. One more time. Don't listen to me. I have a fixed point and I have the arbitrary point. That's what I need for my slope, right? So let me try it one more time. Sorry. 1 y minus 1/2. I know that point is on my curve. The slope is using the f of a and the 1/2. So I'm going to get my slope from f of a. Jeez. Wake up, Robert. Minus 1/2. All divided by x minus a. There's my slope. And I'm multiplying that by x minus 1. Oh my God, what the hell's wrong with me today? Why is it not working? Oh! I know. A minus 1. There it is. Finally. Sorry. You'll see the dynamic one that I'm asking you to doing is a little simpler, okay? And just because I'm improvising here that I'm making mistakes. So you can see here, and let me change my color for my secant line. The secant line, I'll make it purple. So there's my secant line. And so what I'm doing is I can see that I'm going to try and move that green point to the blue point. And as I can get it closer and closer, it looks like I'm only hitting at one point, right? And so I'm guessing at those slopes to get the slope of the tangent. Okay, let me see if I can save a little face here. I've got my function drawn. It's in red. I got a fixed point, 1/1/2. Yes, I've seen a question.
Yeah, I was wondering, so we simplified from m secant to m tangent. If we use the 1 over 2 times 1 plus x, and we like put a into that.
Exactly.
And put
exactly a and exactly. So if I use that simplified secant slope, right? Remember, I'm getting this new x value, this arbitrary x value, closer to 1. And that's what a is doing. A is moving closer to 1, whether I move from the right or from the left.
Yeah.
Yes.
If I just did 1 plus a and put that there instead of the m.
Exactly. But and I want you to think of, right? So what I just finally put in was y minus 1/2, right? Some fixed point, some fixed y value. of f of a minus 1/2, arbitrary point y2 minus y1 over a minus 1 all times x minus 1. Remember, the x and y are my actual points on the line, every one of them. That's why the whole line's showing up, right? F of a is arbitrary, and then 1/1/2 is fixed, right?
Okay. Nothing easy.
Yep.
Thank you.
Yes. So I know it's a little confusing, but it's going to be confusing too when you first do it, right? And if you look at my my other one, it's even more dynamic because both points are movable, right? So just try that and you'll see. So can I calculate secants here with this? I'm going to try and improvise a little bit here. This could be dangerous. Let me see what happens if I just calculate f of a. Yes, it does. F of a minus 1/2. See, it's giving me a number there divided by a minus 1. And you can see my secant's giving me, you can see my calculation of my secant is giving me a prediction, right? So right there, can I move it with my mouse, my cursor? No, I can't. So I can, as a is moving, so you can see I'm going to be sliding a closer. So there's 2.5, and I can see my prediction for my secant slope. And then I can go to 1.7, see my prediction, 1.2, see my prediction. Right, I'm trying to get as close to 1 as I can. And you can see, we already knew it was 1/4, right? I did it in class. So I can see I'm getting closer to 1/4 from the right. And which is making me think that the slope of the tangent line is 1/4, right? Okay, so that was last time. Watch the video of me doing this dynamic secant line. It'll be a little bit, I did it in the afternoon, so I wasn't as tired, so it'll be a little bit clearer. Right now, you're just trying to mimic what I do on that dynamic secant line video so that you can start thinking about what's actually happening. That's what I want you to do. Think, right? See if you can make the connection. Okay, here we go. New stuff, right? There's nothing for me to do, no homework for me to do, correct? So we're working in section 2.4 today. We're talking about another way to find a limit, and this is called the squeeze theorem. So our whole thing today is 2.4 squeeze theorem. And it's not so much the process. It's not so much the process. Oh, maybe my squeeze theorem is not. No, my squeeze theorem is still in 2.3, I think. Or is it 2.2? I forget. Doesn't matter. 2 point something. It's probably 2.3. 2 point question mark. Squeeze theorem. I want to look at the limit as x goes to 0 of sine of x over x. And it turns out that this particular function is a slope, right? So let's look at our sine function real quick, right? We know that at every pi over 2, right, we have a min, max, or 0 of sine, right? You can see the sine function here, right? Yes, you with me? And of course it continues left and right, right? And so what I'm claiming this particular limit is talking about is the limit at 0, 0, and then some arbitrary point, x sine of x. And again, I'm looking at that tangent, that secant line, right? And of course, I want the tangent line. I want this one. How we doing? We okay here? Nice. So what's the slope of my secant line? Who can tell me? What's my slope there? Arbitrary minus fixed in y's over arbitrary minus fixed in x's, right? y2 minus y1 over x2 minus x1, right? Yes? So what's the arbitrary y value here for my green line?
Sin x.
Yeah.
Sin x.
Sin x, nice. And what's the fixed y value for my green line? Not moving. Right? Remember, I want the tangent at 0, 0, right? So my fixed point is 0, 0, right? So sine minus 0 over x minus 0, which of course you notice is our function that we're interested in, sine x over x, right? So this particular function, as x is getting closer and closer to 0, will give me the slope of the tangent line, right? Yes, you with me? Nice. So what would be my secant line? What would be my secant line? Y minus what?
Sin x over x.
Yes. Well, y minus 0, right? Equals the slope of that secant all times x minus 0, right? So y equals m sub sec all times x. Pretty simple, right? Yes? Pretty darn simple. Now, when I put it into Desmos, what do I want to put in for sine x over x? I want to use sine a over a, right? Remember, I've got to have that be my arbitrary point, y sub 2, x sub 2. So hopefully it's a little bit easier to deal with now that I've done it once. Let's see if I can do a brand new one, right? Nice. So my f of x is going to be sine x all divided by x. Oh, sorry, my function is sine x, right? And I want to put in that fixed point 0, 0. Is seeing the sine function on the screen here stressing anybody out? Trig, stress anybody out? I want to put in my fixed point. Yeah, Opsun, question.
Okay. Since it's sine of x over x and we're multiplying by x, if we put y equals sine of x, would it like mess with the
Yeah. So we got to be careful. We got to be careful about putting this directly into that, because then yes, the x's just cancel, right? But we're trying to find the equation of a straight line. So when we use our slope, it's got to be with that arbitrary point in it. It's got to be with that arbitrary point in it. Okay. So let me go back to Desmos here. Good question, though. A comma f of a is my sine, right? So it's using my sine function. And there it is. I already know my equation. I can put it in right away. Y equals f of a over a all times x. There's my dynamic secant line. I'm interested in on my page just looking at the calculation of the slope, f of a over a. It's not going to come to you until you sit there and create this. You're going to All you got to do right now is trust that what I'm doing is correct. But look at what happens when a goes to 0. Remember, that's what I'm interested in. Where is this thing going, right? So I think I can get a little bit more detail if I go between -1 and 1 by a step of 0.01. I think I can get a little bit more detail there. So look at what I'm doing. So now 0.85, look at my slope there, 0.88, right? At 0.71, my slope is 0.9, right? You see what I'm doing? I'm trying to get that a value closer to my fixed point where I have my tangent. And you can probably already guess. Look at it right now. It doesn't look like it's changing at all, but it's changing a little bit. Where's it going? What number do you think it's going to?
1.
1, exactly. So as I get closer and closer to a is 0, my slope is getting closer and closer to 1. So that was my whole point in this, is I wanted to be able to say to you that the limit of sine of x over x as x goes to 0 is 1. That's all I wanted to say. And this is something we're gonna memorize this. Right. Our equation of our line is our first tattoo. This particular limit is our second tattoo. By the way, when you take your test, you're allowed 1 page of anything you want on it, notes, front and back. Okay, when you take your test, test 1, chapter 2 test, you can bring 1 page with you. It should be very clear that there is only 1 page on your desk. That is your notes, and 1 page on your desk. That's the problem you're writing on, right? The problem you're working on.
I'm confused. Like, is a page of written things that I written?
I don't care where you get the page. I personally would write 12 pages, scan them with Cam Scanner, take pictures of them with Cam Scanner, and then save as a PDF. Print my PDF with 6 pages per side.
No, not that. Like you said that we are allowed 1 page, like
1 single 8.5 by 11, anything you want on both sides. In fact, even I'll let you use the edges too. So 4 edges and 2 sides.
So like we can have notes on the test.
1 page of it could be inspirational lyrics, Pedro. It could be your favorite recipe. I don't care. Whatever you want.
Okay.
Okay. I can't, and here's the deal, is I can't stop you from using notes. How the hell could I stop you? I'm not going to have you scan the room and see what's taped on the wall. So, I'm going to...
Professor, one of my old professors made us do exactly that. She had like 2 cameras, and like she made us the test. Literally, we needed to pick like the cell phone and walk around the room and show everything to her.
Yeah, I can't do it. So I'm just trying to make it so that you're more organized, and that it's a fair shot for everybody, so everybody can have 1 page, right? I'm asking you to create it. I will collect it, in the scan. I'll collect it. I want to see what you're writing on it. Sometimes I'll get a question and answer that I'm like, what the hell? What'd they do? Right? There's no way. Where did they learn this? And one time I found it on their formula sheet. So I trusted that that's how they understood it, So anyway, let me get back to work here. This is a nice one to do numerically. So I would ask you all to do this one numerically on your own. You can see I've already kind of done it numerically. On Desmos, I did f of a over a, right? But I want you to do it numerically on your calculator so that you're used to checking things numerically on your calculator. Again, I won't ask you to do anything numerically like this on the test, but it's for you to know you have it right? That's why we're putting in these double checks. All right, I want to look at the squeeze theorem, and then I want to prove that this particular limit is 1 using the squeeze theorem. Okay? Everybody with me here? Everything okay? When I did that second secant line, was it a little bit clearer? First time I probably confused a few of you. The second one was a little clearer. Thank you, Talia. Thank you. I love to see your faces because I can just see you nodding your head like we're in a classroom, right? So, all right, I want to talk about the squeeze theorem. There's a nice video of this by Khan Academy. I like Khan Academy a lot, but he puts me to sleep. So I'm always looking for, as a student, I would say you go find someone who does calculus examples and lectures and who doesn't put you to sleep. Like some people like that organic chem tutor guy. I like this one grad student from, I think she's in Harvard or something. But you find someone, she writes on the glass. Looks like she's just writing in the air. But you find someone that doesn't put you to sleep, right? Especially if I put you to sleep. So squeeze theorem. It says that as x goes to c, if I have a couple of functions, right? Let's say f h, right? So I've got a function f of x, a function h of x, and then I've got some other function g of x. Okay, and you can see what's happening. You can see at that point I'm interested in, I'm crushing down to a single height, right? Do you see it in the picture? You see the blue point going to that height, but above everything else. The green going to that height, but below everything else. And the red, who cares what it's doing in between, as long as it's staying in between those two functions, right? So it says if f of x is greater than or equal to g of x, which is greater than or equal to h of x, right? As x goes to c, then what are we saying about f and h? They're going to a limit, right? They're going to the same height, so h has to go to the same height, right? If the limit as x goes to c of f of x equals the limit as x goes to c of h of x, if my upper function and my lower function squeeze down to a point, then the inside function has to as well. I'm sorry, it's if, and then it's a then. So if the upper function is greater than the middle function, greater than the lower function, as x goes to c, and the limit at the top and the bottom are the same, then the limit of g of x as x goes to c is the same. Right? We get the idea. If that upper function goes to a limit L, the lower function goes to a limit L, right? So the upper and lower go to the same height, then that inside function has to go to the same height. And so what's going to be special about this is going to be easy to find these two limits. These are easy. And this one's not so easy. So if I can find the easy limits, then I've got the not so easy limit. All right, let's look at an easy picture of this, right? So let me go back to Desmos. So I'm going to use sine and tangent, right? And then my inside function is going to be x. Okay, so I'm going to use sine and tangent, and my inside function will be x. Yes. So I just want to notice. I want to notice that sine of x is greater than x, which is greater than tan of x. And it's hard for me to see that, really. Oh, and I've got it opposite, sorry. Tan of x is bigger than x, which is bigger. Right, so tan of x is in green. As you see it above the blue, blue is x, and then blue is above the red, right? So tan of x is greater than x, which is greater than sine of x. Yes? So I already know that tan of x is greater than x, which is greater than sine of x, right? In fact, we'll say greater than equal, because that's really what it has to be at the limit. It has to be equal, right? So clearly true, right? Everyone with me? Yes? And there's a beautiful way to generate this without just going right to the graphs, but this is the easiest way to do it. So I'm just trying to save a little bit of time here. I usually do the more difficult one, but it always confuses everyone. But this is not the limit. So this squeezes down to 0, doesn't it? What's the limit of tan of x at 0? It's 0, right? What's the height of sine of x at 0? 0. So these two things squeeze down to 0. So that means y equals x has to squeeze to 0. But did I need the squeeze theorem for this? No, I already know how to do the limit of x. I already know how to do the limit of this middle function, right? But what's the function I want? Do you remember from the very start of the lesson? What's the function I actually want? What was that limit I'm interested in? The limit as x goes to 0 of something is 1, right? I showed you with the secant line that the limit was 1. But what was the function? Do you remember?
Sine x over x.
Yes, sine x over x. So I want to turn this function into sine x over x. What do you think I should do? I want to manipulate this algebraically to get that middle function to be sine x over x. What do you want to do? I want to go have breakfast. What do you want to do mathematically? Come on, take a chance, please.
Can I replace it by 0?
Okay, but that would be me getting the limit right away, right? Remember, I want it to become this. I want that middle piece to become this, right? So what do you want to do? Well, should the x be in the numerator?
By x.
Divide everything by x would give me 1 in the middle, right? And it would give me sine x over x here. I like the idea, Alan. I like it, but I want to squeeze on sine x over x, so I don't want it to be on the end point, right? So try something else. But I like that. Thank you. Well, I'm just going to take a reciprocal, right? So I get 1 over the tan of x is less than or equal 1 over x, which is less than or equal to 1 over sine of x, right? And yes, I could change to cotan and cosecant, but I'm not going to do that yet, right? So now I'm almost there. And what's my last thing I have to do here?
Multiply each function by sine x.
Nice. Thanks, Noel. So multiply by sine x, right? So I get sine x over tan x less than or equal to sine x over x less than or equal to sine x over sine x. Nice. Beautiful. I got what I want in the middle, but I want to manipulate the sides a little bit, right? So on the right-hand side, it's obviously 1, right? So in the middle, I've got sine x over x, and on the right, it's 1. That's nice, because that's an easy limit to get, right? What's the height of 1 as x goes to 0? 1. The right-hand side is going to stay the height of 1, right? So I'm squeezing the right-hand side down to 1. I want the middle to squeeze to 1, right? So let's see what happens on the left. Anybody notice what I get? Sine x over tan x is what? Sine x over cos x, which is what? Sine x times cos x over sine x, which is just cos x, right? Remember all the fun you had in pre-cal doing those trig identities, right? That you're going to do that a lot in Calc 1, even more in Calc 2. So if the trig identities were an issue for you, go back to that section of your pre-cal book and do every trig identity there, right? So this side becomes cos x. Is everybody okay?
So I get the math we just did. That was fine. Why did we want it specifically x to become sine x over x?
Because that was my function that I showed you had a limit at 0 of 1 with the secant line. But now I'm trying to use this squeeze theorem. So I don't know how to show you how this limit is without doing it numerically, right? So I'm trying to give you options to do limits algebraically, right, using the squeeze theorem. Yeah, so what I'm doing is I'm getting an upper function and a lower function that I can evaluate, and then I know that the middle function has got to go to the same place.
Okay, and because it's the same problem, we had the secant from before.
Yes.
But tangent, we just thought of, and x we thought of.
No, I cheated. My teacher taught me this, and their teacher taught it to them, and so I'm just passing along some useful knowledge, right? And of course, we don't always listen to our parents. I'm kind of your mathematical parent, right? Don't smoke pot. But we don't always listen, right? But I'm asking you, again, I want you just to have this limit memorized. The limit of x goes to 0 of sine x over x is 1. I want it memorized. I'm trying to give you the understanding. Yeah. Nice. So this limit I can do the limit as x goes to 0 of cos of x. And I know that's got to be the limit as x goes less than or equal to the limit of x goes to 0 of sine of x over x, which is less than or equal to the limit as x goes to 0 of 1. What a waste of time that is. But what happens on the left side? Can I plug in? Can I plug in on that limit on the left?
Yes.
Yeah, Marcus, thank you. It's cos of 0, right? Which is what?
1.
1, yeah. So look at what I got. I got 1 is less than or equal to the limit of sine of x over x, which is less than or equal to 1, right? The limit of 1 as x goes to 0 is still 1. And there it is. I've got it, right? Right? 1 is less than or equal to the limit as x goes to 0 of sine of x over x, which is less than or equal to 1. Done. Proven by squeeze theorem. I am not going to ask you to do a problem by the squeeze theorem. I'm going to ask you to apply this squeeze theorem. Okay? So again, what's the main thing here? I don't care if you understood anything I did, memorize that limit. Memorize that limit. All right, I've got one more little theory piece to do, and then we can look at a problem. Okay? So our last little piece of theory here is it okay if I move on? Everyone all right? My last little piece of theory that I want to do is from 2.3, properties of limits. And I think these are pretty obvious. Okay, I think these are pretty obvious. But if you're interested in proofs of these, I have actually videos of the author proving them. If you're a math major, you're interested in the proofs. If you're a computer science major, probably interested in the proofs. The rest of us, we don't care. And since that's the case, I don't put any proofs on the exam, right? So, but it says the product of the limit of a product is the product of limits. The limit of a product is the product of limits. Linus and Lucy. So let's assume, and of course when you assume you make an ass out of you and me, right? Assume that the limit of f of x as x goes to c is L, and the limit of g of x is k, right, as x goes to c. Then we're saying that the limit of f of x times g of x as x goes to c is the limit as x goes to c of f of x times the limit as x goes to c of g of x equals L times k. That's my theorem. And it should feel comfortable to you that this is the case, right? Especially if I look at a real simple version, right? Let's say the limit of x times x squared as x goes to 2. That's definitely 8, right? It's x cubed, right? And I can just plug it in. There's no problem in plugging that in. But what happens if I look at the limit of x as x goes to 2, sorry. And if I look at the limit of x squared as x goes to 2. Those are also obvious, right? This one's 2 and this one's 4. And look at the product. 2 times 4 is 8, right? So, but the trick is, so I'm not going to prove it to you, but it should be obvious to you, right? But the trick is, how do you separate the product, right? That's going to be the trick, right? And so we're going to look at our first problem here, okay? Everybody with me? So, by the way, read those limit theorems in section 2.3. Read them all. They should all make a lot of sense to you. The limit of the sum is the sum of the limits. The limit of a quotient is the quotient of the limits, right? All of things that should make sense. They should all just make common sense to you. The proofs are all epsilon delta proofs, okay? So in the past I have spent some time proving some of them, but I don't want to use the time if I don't need to. Why does it make sense though? Why does it make sense? Because what are we talking about? What are limits again? Remind me. What is a limit?
So like the prediction of the value at a certain point.
Sure. So the value of a function or the height of a function. So if I have a product of two heights, it's just the product of the two heights, right? It's some new height. So it really shouldn't be a surprise. But the trick is always going to come from how do I create the right separation in the product, right? And so in our schedule, for today, I am asking you to, and I'm just looking at another screen here. Give me 1 second. In our schedule for today, I am asking you to do on test 2 review all of my problems. Come on, why is everything so slow? In test 2 to review all of the problems in number 4 and number 5. Okay. So I'm asking you to open up test 2 review. Have you noticed that I put all the chapter 2 tests up yet? And inside of chapter 2 is a test 2 review, and I think there's something else. And then I have chapter 3 up there, all my tests for chapter 3, and I think I have all my midterms up there. So why would I put the midterms up there? Because you can also look at my midterms and extrapolate the chapter 2 material off of that and do those, right? It's a lot to do, okay? I know that. It's a lot to do. But again, you're going to do as much as you need to get an A, and that's going to be a little too much at the beginning. And it's not until chapter 3.6 that it gets difficult, okay? So just so you know, at 3.6, if you get lost, then you got to really kick it in. Okay. Okay, so let's do our first problem using the squeeze theorem. So I want you to use the fact that the limit as x goes to 0 of sine of x over x equals 1 to find the following. The limit as x goes to 0 of sine 2x over x. So remember, I'm asking you to do that sine x over x as a numeric, right, on your calculators. So if I gave you something like this on chapter 2 test, our first test, it's a perfect thing to do to verify that you got it right. But then we want to do some algebra. So who's got an idea here? Do you recognize anything from pre-cal?
Double sine.
Yeah, the sine 2x is what? What function is that? Do you remember? Alan, right? I kind of tortured you with these, right? These trig identities.
2 sine cosine?
Yes, 2 sine x cosine x. 2 times sine x cosine x. Now you can see I have a product of functions, right? I have a product of functions that are good for me because I know which one I want to use. I want to use sine x over x. So I'm going to split this limit into two limits of sine x over x times the limit as x goes to 0 of 2 cosine x. The art is splitting them into pieces where you know how to evaluate the limits, right? And it's usually you're just always looking for this piece, always looking for that piece, right? So I know that first limit. What is that first limit? What is that first big green limit? 1. And then how do I evaluate the other limit? Cos of 0, right? 2 times cos of 0. And what is 2 times cos of 0? Cos of 0 is 1. Everybody okay with that?
Yeah.
By the way, I really want you to be able to draw me a quick picture of sine and cosine all the time. Sorry. Be able to draw a quick picture of sine and cosine so I can see, right? Sine of 0 is 0. And cos of 0 is 1, right? And so what do I get as my answer 2? So the limit as x goes to 0 of sine of 2x over 2 equals 2. I get this every semester. If you give me this, I'll take extra. I had a professor in college. I went to Rutgers, and if you got something wrong, he'd take extra points off. So if the problem was worth 10 points and you got it wrong, you wouldn't just get a 0. You'd lose another 10. So you could get a negative 100 on one of his exams. Bastard. So I get this all the time. I get the limit as x goes to 0, sine of 2x over x is the limit as x goes to 0 of 2 times the sine of x over x is 2. And this is absolutely wrong because of what? I mean, I got the right answer, right? Shouldn't that be right? 2 plus 1 is 4, right? Oh, it's the right answer. I just spelled it wrong. So what's the deal here with my purple circles? How do I know that's not true?
Oh, I think they're like, I just call them rules, but if this was sine x like squared, that would work, right? Like we could put 2 in the front.
No, that's you're thinking of the natural log. You're thinking of logarithms, where the exponent becomes a coefficient, right? Yes. What's the problem with this? What is the problem with those two circles? Why are they not equal? It's from our pre-cal days.
You're multiplying 2 times sine x, and the other one is you're multiplying x times 2.
Yes, but it's inside of a function, so it's I think I would like it's a little bit more of a sophisticated answer than that.
Is it like that when you say sine 0 equals 0?
Yes, both of them are 0, right? Sine of 2 times 0 is 0, and 2 times sine of 0 is 0, but it still doesn't make it right. It's about the graphs of those two functions. What do the graphs of those two functions look like? Function A and function B. Function B is called amplitude modulation, right? 2 times the sine makes the radius of the sine function 2, not 1, right? So there's y equals 2 sine x, amplitude modulation, right? Like this is sine x, right? So y equals sine x. There's an amplitude of 1, radius of 1. 2 sine x is amplitude of 2, radius of 2. What's the other one do? What's this one do? Sine of 2x.
Is that the period?
Yes, it's called frequency modulation. Yeah, it cuts the period by 2. So I see this, right? So I'd see the sine function twice, y equals sine 2x. So clearly the black and the green functions are not the same, right? The graphs are not the same. So the functions are not the same. You can't do that. Just know, you can't do that. But I can do this limit another way, and it's a good trick to have, okay? And you need this other trick, okay? So I want to do the same limit another way, the same problem another way. Again, assuming that I know that the limit of sine of x all over x as x goes to 0 is 1. So we're doing the limit as x goes to 0 of sine of 2x over x. And my trick is to make a theta substitution. You'll see we'll do all kinds of substitutions in calc, this whole calc sequence. When things are complicated inside, I want to make them look simple. Okay? So I'm going to let theta equal 2x. And it's really important that you see that the limit of theta as x goes to 0 is also 0, right? Do you see that? Because it's just 2x, right? 2 times something really close to 0 is close to 0. So theta is going to 0 here, right? What I can really do is solve for x. That's kind of a nice thing to do here, right? So if theta equals 2x, what does x equal?
Theta over 2.
Nice. So then I make my substitution. So the limit of theta going to 0 is now sine of theta over 2, right? Kind of cheating a little bit here. I probably should have put a theta over 2, but it doesn't matter. If theta over 2 is going to 0, theta is going to 0. So now look at what I have. I have 2 times the limit as theta goes to 0 of sine of theta over theta. Why can I bring that 2 outside of my limit? Why do you think that 2 can move outside of the limit? Why can that 2 move up to here? Well, I know keep, change, flip, it moves to the numerator. But why does it move outside of the limit?
Is it because of cross product?
I kind of did a limit in my head, if you will. It could be. Who said that? Was it Markins? It could be. I don't know if I know the physics that well when we're talking about cross product. But if you're saying cross multiply, yeah, I said that part's obvious. But why does it come out of the limit, right? So, but think about it. It's I have a product, right, of 2 times some other function. What's the limit of that 2? What height does that 2 move to? It stays at 2. So it's like I'm kind of doing that limit real quick. And so what do I know about this limit here in the box? What's this limit? Does it matter if I use the letter X or a Greek letter or no? So this is 1, right? So we get an answer of 2. So one of the things I want to say more about section 2.3 is that coefficients move in and out of limits. Coefficients move in or out of limits. Meaning, if the limit of as x goes to c of f of x equals L, then the limit as x goes to c of a times f of x is a times the limit of c as x goes to c of f of x equals a times L. Constant can move in or out of a limit. Coefficients, constants. Not variables. Variables cannot, right? Because variables have change heights, right? Constants don't change heights, right? You with me? This is a really easy proof. Because imagine what's happening to a times f of x minus a times L less than epsilon. Can you see what's happening there? What's going to come out of there? What's going to factor out of this part?
A.
Yeah, I'll factor out an absolute value of a, right? So I've got, now I have a delta for this part, and then all I have to do, right? All I have to do is change my delta by a little bit, right? All I have to do is change my delta by an absolute value, a factor of absolute value of a. And then I get the right delta for this new limit. This is a little abstract, so if it's bothering you, don't let it bother you. But okay, so here we go. Ready? Let's find the limit as sine of x sine of 3x over 2x. So I want to do a couple of things here. First of all, what do I want to do with that 2? Remember, I want my thetas to match. I want sine of theta over theta, right? So I could do this one with saying theta is 3x again. Okay, I could do that, but I want to do it a little differently. But I want those things to match. So I want a 3x upstairs and I want a 3x downstairs. I don't want a 2x downstairs, but I can move constants out. So tell me what comes out of this limit. Sorry, as x goes to 0. Where does that 2 go? This is a limit. Where does that 2 go? Man, there's some great creativeness today. I know it's early. Feels like a Monday. I don't know. The 2 comes out, right, as a 1/2. Yes, you agree? Constants can move in or out. Constants don't change height, so it's like I'm doing a limit there and just not showing the work. But I want to move a 3 in downstairs, correct? I would like the downstairs to say 3x. Are you seeing that at least? Yes, 2 of you, 3 of you. 4 of you. 5. Thank you. So I'm going to multiply by 1 because I can. Am I allowed to always multiply by 1? Yes, I can always multiply by 1. Even 1 times, I got a 1 right here. 1 times me is still me, right? But remember, I want I want downstairs to be a 3x, so I'm going to move this one in. Move it in. So I got 3/2 times the limit as x goes to 0 of sine of 3x over 3x. What is this limit now? What's that box? Don't I have sine of something going to 0 over something going to 0? So it's 1. So I get 3/2 times 1. Final answer is 3/2. So you saw me do this 3 different ways. I used a trig identity, I used a theta sub, and then I'm using the fact that this constants can move in or out. So I can manipulate things using just constants. All right. I think we did enough for today. So you've got homework to turn in Monday, right? It'd be a good idea for you to get on the CAM scanner right away. Even if you don't feel like you can get the homework done until Sunday, you should make sure the CAM scanner is working and get back to me if you have trouble with it, right? Tally, thank you for sending that. It looked like it worked pretty easy for you.
Another way, Professor,
Yes.
good way, we scan PDFs that I know. You can use, if you have iPhone, the notes from my phone.
Exactly. That's another way to do it. What I'm worried about is often when I get things from notes, and you can see, so the video I put out there didn't do what I'm asking you to do, but if you give me some file that's so large that you can't download it and have to share it with me, I don't want it.
Normally what I do, like, I think I already submitted the PDF that, like, have more than 5 pages. Normally, I just, like, pick the notes and send by mail to myself and send by mail to the professor.
That's what I want. I want to make sure that you can attach the PDF to mail, because I don't want to have to download it from your OneDrive or your whatever. I want to just, open the email and have the PDF right there. And so the PDF's safe, easy for me to write on so I can correct it and send it back to you, that type of thing. I'm sorry, Gubran just said something here. if you miss a test, you miss a test. What I usually do is replace a chapter test with the final exam grade. So if you miss test 1, I'll take the test 1 material off the final exam grade and give you a final a test grade. If you miss 2 tests, then there's nothing I can do. You get a 0 on 1. So I would say don't miss any test, but if you have to miss a test, you have to miss a test.
Professor, what's the homework?
It's on Blackboard. It's 4 problems, 3 of them from 2.3. Can you make sure you look at it now, please, Pedro?
Oh yeah.
Open Blackboard. Go to the homework tab.
Okay. Section.
Yeah, we all can read. You don't have to read it to us.
Like the section the problem, but like why are you open the problem?
It's in the textbook. In the textbook.
Oh, okay.
And the answers are in the back of the textbook.
And the PDF that you gave us, yes, the textbook PDF.
Yes.
Okay.
But use the actual. You can do the PDF textbook I gave you, or use the full textbook in WebAssign. Does anybody need to see that?
Yes. I'm still not Professor.
Yeah. So I'm going to just open the full textbook here. Blackboard, right? No, WebAssign, sorry. WebAssign.net. Oh my God, it's so slow. It's driving me crazy. So by the way, if you don't need to see this, this is the last thing I'm doing today. Have a great day. I'll see you Friday.
Homework's also in the PDF textbook.
Yes,
the right?
The PDF I sent you is the full textbook. When you just go to WebAssign, it's a stripped down version, but there's a full version there. That's what I'm showing right now. So I'm just trying to log in. It's just so slow, and I don't mind it if you're okay that you go. I'll see you all Friday. Don't worry about it.
Your homework's for Friday or for Monday?
Always on Mondays, so you'll always have. I'm hoping to always give you at least a full week to do homework. And if you notice, you had a chance today to ask about any numeric limit. Algebraic limit. So I'm always going to try and give you a chance to ask questions before anything is due. Okay. Here's our class. Here's the ebook, right? Now, if I open this ebook, you're going to see, I might have to click a couple times here. See, it opens it. It's something called MindTap. And that's kind of like a stripped down version of our textbook. And I think it's a lot easier. Oh my God, it's so slow. There we go. It's a lot easier over on the right-hand side here. You see this little textbook on the right-hand side? That's the full book. So that's an exact copy of that PDF I sent you. Okay? So if I open that full book, I can see right chapter 2. I could jump to the section of that book, and then down at the bottom here in the appendices. Let me open the appendices. I'll see the answers. Okay. Oh my God, so slow. So in one of the appendices it says answers to odd problems, and I'm only going to be assigning odd problems to you. Oh, this is better. Go to the table of contents of the full book. And it all gets scrunched down into this MindTap screen, which is why I gave you the PDF, right? Because you can just open the PDF and you get the full thing with the table of contents on the whole page. It's a lot easier. Yes, I've seen. Yeah, that's fine. So let me see if I can open table of contents here. There we go. It might be reference pages. But let me see what appendices say. There's some proofs. Here's a whole bunch of reviews of things. Right, there's the epsilon delta if you want to read that. Here's a nice review of trig. So it's not in the table of contents. It's not in the appendices. It's in the that next thing on my list. It's just so slow. Reference pages. And it didn't open to the right place. We'll try it again. Table of contents. Reference pages. There we go. Where is it? Damn it. The answers are here somewhere. I'll find them. Okay. I will find them and I'll post them in a Blackboard announcement. Okay. Let me do that.
Okay, so like on Blackboard, I have to go on homework and I find like what you assign.
Yeah. So, yeah. In Blackboard, I put up a new sidebar of homework. Can you, Markins? Can you open your Blackboard right now and just see it?
Yes, I can. Yeah, I see it. I see homework in section.
Yeah.
Right?
Yep. So there's three problems to do with algebraic limits from 2.3, and one problem to do with numeric and algebraic in 2.1.
So, okay, so the algebraic limit like is 3 problem, right?
Yes.
That's in 1921,
Yep.
right?
Yep.
Okay.